A radioactive substance decays at an annual rate of 13%. If the initial amount of the substance is 325 grams, which of the following functions f models the remaining amount of the substance in grams t years later? A good first step is to size up the problem. We're told that the initial amount of the substance is 325 grams. And we're also told that its annual decay rate is 13%. So to understand the decay rate means that this radioactive substance loses its quantity by 13% every year. And let's now see if we can put together a function that would define this process. Before we come up with a mathematical function to define it in terms of t years from a certain point, let's first understand it in very approachable near-term numbers. So what we get is that if our substance loses 13% every year, it means that it keeps 87% of its quantity. So let's put it down like that: 100% minus 13% that it loses, and we keep 87% of the mass. In order to find how much we will have 1 year from the point of initial deposit of this radioactive substance, let's try to understand how mathematically we can represent 87%. If we had 325 grams and it did not lose any mass, then we would multiply 325 by 1 and we would get 325. However, it is losing its mass, and that means that 87% of the amount is represented by the number of 0.87. So if we are to multiply 325 by the number of 0.87, it is the same as saying that we keep 87% of this amount, 325. So let's put it down in these numbers. Whatever amount we get after 1 year, which is 325 times 0.87, that amount, it's in the brackets right now, will be multiplied by another 0.87, which means that of the remaining amount, only another 87% will remain. Since the initial amount of 325 grams has been multiplied by the same number of 0.87 twice, mathematically it can be represented as 325 times 0.87 squared. In the year 3, the remaining amount is multiplied by another factor of 0.87, which represents the preservation rate. As a result, we can see that 325 has been multiplied by the preservation rate of 0.87 3 times. So mathematically, that is 325 times 0.87 in the third power. Now let's reflect. In year 1, 325 was multiplied by the preservation rate of 0.87 once in the first power. In the year 2, 325 has been multiplied by the preservation rate of 0.87 twice, or in the second power. In the year 3, the power is the third power. So taking note of this, we can predict that in the year t, whatever that year may be, 325 will be multiplied by the preservation rate in the power of the number of years that passed since the amount was initially deposited. Let's now refer to the answer choices provided, and answer choice A seems to fit our function that we defined below, that in the year t, we're getting 325 times 0.87 in the power of t. Functions are normally notated by the letter f. Sometimes other letters may be used, but most frequently you'll see the letter f. And in the brackets, t represents the number of years that has passed since the radioactive substance was deposited. Our correct answer is answer choice A.